Magandang gabi mga ka-spacers! Gusto nyo bang malaman kung paano nagsimula ang astronomy? Gusto nyo bang malaman kung paano nag-stargaze at nag-aral ang ating mga ninuno tungkol sa astronomy? Ngayon, kung gusto nyong malaman, then dapat tapusin nyo itong video na ito. Episode 5 of Space, the Final Frontier. Please like and share this video para po makatulong tayo sa mga estudyante na gustong mag-aral ng siyensya. So tara na, huwag na tayong magpatumpik-tumpik pa. And let us go where no man has gone before.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone.
There she is. NASA's Voyager 1. Launched in 1977.
But that's just very small potatoes compared to what the Earth is involved with and knows about.
We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
One small step for man, one giant leap for mankind.
Good evening mga ka-spacers and welcome to episode 5 of Space, the final frontier. This is Professor Jun Cahigal. Now, Space, the Final Frontier is a series of online lectures intended to inspire our students out there to love the sciences, especially astronomy, and to guide them in their online classes. So, in today's episode, episode 5, we will trace the beginnings of modern astronomy starting during prehistoric times up to the development of the three laws of planetary motion of Johannes Kepler. And if you have any questions, comments, or reactions about this lecture, please do not hesitate to type in your questions or your comments or your reactions. We would like to hear from you. So kung may mga katanungan kayo or any reactions about this video, please do not hesitate to type in your questions or your comments or your reactions in the comment section. Please like and share this video para makatulong po tayo sa mga estudyante na mag-aral ng siyensya. Alright, so let us not waste any more time and let us go back during the prehistoric times where no man has gone before. Hello, greetings. I am Professor Jun Cahigal, and I would like to welcome everybody to this virtual lecture entitled The Origin of Modern Astronomy. So in this lecture, we will trace the beginnings of modern astronomy. And we will start our journey way back during prehistoric times. So for tens of thousands of years, our ancestors, they have started looking up in the night sky, and they were fascinated by what they saw. They saw stars, they saw the moon, and they were fascinated by these observations of the sky. And our ancestors, they also noticed certain patterns of stars in the sky. And these patterns of stars, they look like animals and people. And because of their amazement and fascination of these patterns of stars, they made up stories about what they observed. Alright, and they noticed that the moon also changed shape from night to night. And also they noticed that the moon changes position among the background of stars. So they started observing the night sky, and probably they made records of what they have observed. In fact, the oldest records we have of these ancient astronomical observations are the 30,000-year-old paintings found on the walls of caves. So here is an example of an ancient cave painting made by our prehistoric ancestors. So we have here a painting of a prehistoric ox or cattle, and in the background you will notice dots. Okay, and probably those dots, they represent constellations or these patterns of stars in the night sky. And they were fascinated by it, so they made these cave paintings. Alright, and in this picture, if you will notice, look at the head of this prehistoric cattle. You will notice that there are dots. And probably, if you will just analyze the pattern, they resemble the constellation Taurus. And in front of the cattle, you will notice 3 dots. And probably those 3 dots, they represent the Orion's belt. And just above the painting of the ox, you will notice those patterns of stars, and probably they represent the constellation Pleiades. Fascinating, isn't it? Amazing, really. So some of the world's oldest cave paintings have revealed how ancient people had relatively advanced knowledge of astronomy. So our ancestors, they started looking up, and out of their fascination and amazement of what they saw in the night sky, they made these cave paintings. So this would reveal that they have some advanced knowledge of astronomy. Fascinating, isn't it? Alright, so those were the cave paintings made by our ancient ancestors. And again, these cave paintings revealed that our ancient ancestors, they had relatively advanced knowledge of the heavens. And because of their fascination and their amazement of what they saw in the night sky, they associated their astronomical observations with religion, with their gods and spirits. So that's what they did. They associated these astronomical observations with their gods and spirits. So these early cultures, they identify these celestial objects with religion, with their gods and spirits, and also they related these astronomical objects to natural phenomena such as rain, drought, seasons, and tides. Okay, so ladies and gentlemen, you will notice that our ancestors, they place so much importance to observing the night sky because they associated them with their gods and spirits, and these astronomical objects were associated with their daily activities. So you can see now the importance of tracking accurately the movements of these celestial objects. So what our ancestors did in order to track accurately the movements of the sun, the moon, and the stars, they started erecting large stones. So our ancestors at around 5,000 years ago, they set up large stones to mark the movement of the sun and the other heavenly bodies. So one good example of this is Stonehenge. And by tracking the movement of the heavenly bodies, these first astronomers have created calendars based on what they observed in the movement of the moon. Alright? So one good example of an ancient observatory is Stonehenge. Alright, so this is Stonehenge in UK, United Kingdom, in England. And this ancient observatory was also a place of worship. So you can see now the stones that were erected, and these stones were aligned to certain stars. Stonehenge was constructed at around 3000 to 1800 BC. Okay? And the stones that were erected were aligned to certain stars in the night sky. And using Stonehenge, they were able to track the sun and the movement of the stars. With that, they were able to record sunset, sunrise, moonset, moonrise, and they were able to predict winter and summer solstices. Amazing! Fascinating, isn't it? And using Stonehenge, our primitive ancestors probably they were able to came up with a calendar using Stonehenge. Alright, so that's Stonehenge, an ancient observatory and also a place of worship because our ancestors have associated their astronomical observations with religion, with their gods and goddesses. Alright, so that's Stonehenge. Stonehenge is an astronomical ancient observatory, and at the same time, Stonehenge is a place of worship. So you could see here that our ancestors have associated the observations of the heavens with religion. Okay, so another example of an ancient observatory is the Bighorn medicine wheel in the United States. So if you will notice the Bighorn medicine wheel, the markings on the ground resemble the spokes of a wheel. And those markings on the ground are actually aligned to certain stars. Okay? Like Aldebaran, Rigel, Sirius, and the Bighorn medicine wheel was used to mark the movements of the sun, the moon, and the stars. They made use of the Bighorn medicine wheel to predict winter and summer solstices. Fascinating, isn't it? Alright, so that's the Bighorn medicine wheel in the United States. Now, another example of an ancient observatory was made by the Mayan civilization at around 1000 AD, the so-called Caracol, made by the Mayan culture. Now, the Caracol was an astronomical observatory. Okay, it was made to track the movements of the heavenly bodies, and the Caracol also was made to worship their gods. So that was the Mayan civilization, and that's the Caracol, which is an ancient observatory. Alright, so these astronomical observatories like Stonehenge, the Bighorn medicine wheel, and the Caracol, they were constructed because our ancient ancestors, they associated the study of the heavens with religion. And again, they associated the movements of the stars, the moon, and the sun with natural phenomena. So really, the study of the heavens was considered really important to our ancient ancestors. That's why they constructed these astronomical observatories. Now, the Mesopotamians also considered astronomy a huge part of their culture. Astronomy was a huge part of the Mesopotamian civilization. So it was the priests who studied the heavens. And with their knowledge of astronomy, they came up with a 12-month calendar based on the movements of the moon. And also the priest, the Mesopotamian priest, they also predicted winter and summer solstices. They predicted also eclipses. And they were able to come up with some astronomical tables. They amassed astronomical data. Fantastic, isn't it? Now, the Mesopotamians also constructed observatories. Their observatories are in the form of ziggurats that was constructed at about 6,000 years ago. And if you look at the illustration of a ziggurat resembles that of the pyramids of the ancient Egyptians. Now, a ziggurat has 7 levels if you will take a look at the illustration. And a level is dedicated to a particular wandering object in the sky. Like for example, the first level is dedicated to the sun, the second level is dedicated to the moon, the third level is dedicated to Mercury, then followed by Venus, then followed by Mars, Jupiter, and the last level is dedicated to Saturn. Alright? And these 7 levels, they represent the 7 days of the week. Okay, so that was made by the Mesopotamians. Okay, so the 7-day week was made by the Mesopotamians. Okay, so if you will take a look at this illustration of the 7 days of the week, each day is dedicated to a particular wandering object in the sky. Like for example, Sunday. Now, Sunday is dedicated to, obviously, the sun or Sol. Alright? Then look at Monday. Monday is dedicated to, obviously, the moon. Luna, Moon Day. Moon Day. Now everybody look at Tuesday. Now Tuesday is dedicated to the god Tiyu, which is equivalent to Mars. So that's why we have Tuesday. Tuesday. Then everybody look at Wednesday. Wednesday is dedicated to the god Woden, which is equivalent to Mercury. So Wednesday, Wednesday. Then everybody look at Thursday. Thursday is dedicated to Thor. I'm sure you know Thor. Okay, which is equivalent to Jupiter. So that's why we have Thursday. Then look at Friday. Friday is dedicated to the god Frigda, which is equivalent to Venus. That's why we have Frida, Friday. Fantastic, isn't it? Fascinating. And Saturday, look at Saturday. Saturday is dedicated to Saturn. Saturnus, Saturday. Okay, so this was made by the Mesopotamians. So the Mesopotamians came up with this 7-day-a-week calendar. Fascinating, isn't it? So using their ziggurats, the Mesopotamians came up with this 7 days in a week. So each day was dedicated to a particular wandering object in the sky. Alright, so here is an illustration of a ziggurat with those 7 levels. Again, each level of the ziggurat is dedicated to a particular wandering object in the sky. Okay. Also, the Mesopotamians, they used the ziggurat to track the movement of the stars. And they came up also with their own constellations. Okay? And they use these constellations so that they can determine their planting and harvesting periods. So what I'm trying to say is that the Mesopotamians, they believed that these stars can influence their daily activities, especially planting and harvesting activities. So they came up with the zodiac. So the zodiac was made by the Mesopotamians. Alright? Fascinating, isn't it? Okay? The Mesopotamians also divided circles in 360 degrees, which we still use, and they recorded their observations in cuneiform. Alright, so that was the astronomy of the Mesopotamians. Okay, so just like the Mesopotamians, the Egyptians also associated the study of the heavens with religion. Now, the Egyptians, they believed that many of the stars and the planets were actually gods and goddesses that they worshipped. So similar to the Mesopotamians, the Egyptians also associated the study of the heavens with religion. In fact, they were drawn to 2 bright stars that always could be seen circling the North Pole, and the Egyptians referred to those stars as the indestructibles. So these 2 bright stars are the following. We have Kochab in the bowl of the Little Dipper or Ursa Minor, and Mizar located in the middle of the handle of the Big Dipper or Ursa Major. Okay, so here's a simple illustration to help us locate these 2 bright stars in the northern hemisphere. So this is Mizar. Mizar is located at the middle of the handle of the Big Dipper, and this is Kochab, located in the bowl of the Little Dipper. Okay, so again, this is Kochab at the bowl of the Little Dipper, And this is Mizar. Mizar is located in the middle of the handle of the Big Dipper. And right over here, just follow my cursor, this is the North Star or Polaris. Okay. Alright, so those are the so-called indestructible stars located in the northern hemisphere. Now, the Egyptian civilization is anchored on agriculture. Agriculture was the foundation of the ancient Egyptian civilization, so water is vital. And the source of water for agriculture is the Nile River. And the Nile River is affected by the lunar tides. So there are times in the year that flooding occurs along the Nile River. So it is important for the Egyptian farmer to predict the occurrence of flooding along the Nile River. Okay? So the annual flooding of the Nile was the foundation of Egyptian civilization and agriculture. So it is vital for the ancient Egyptians to predict the occurrence of this flooding with accuracy. And this became the driving force behind the development of Egyptian astronomy. Fascinating, isn't it? And again, like what I have mentioned, the Egyptians studied the heavens and they associated the study of the heavens with religion. Alright, that was really fascinating indeed. So the prediction of flooding along the Nile River became vital for the Egyptian farmer. And this became the driving force behind the development of Egyptian astronomy. Okay? And not only that, when we speak of Egyptians, we think of the pyramids. And the Egyptians, they constructed their pyramids in such a way that they align their pyramids and even their temples towards the north. Why? Because they believed that their pharaohs would become stars in the northern sky after they died. So as you could see here that the Egyptians, they associated even architecture with religion and in the study of the heavens. Alright, so the precise orientation of the Egyptian pyramids affords a lasting demonstration of the high degree of technical skill in watching the heavens. It has been shown that the pyramids were aligned towards the pole star. Now at that time, ladies and gentlemen, the pole star was Tuban, not Polaris. Now Tuban is a faint star in the constellation of Draco or Draco. Alright, so as you could see here, see the orientation of the pyramids, they were aligned at Tuban, okay, which is then the pole star during that time. Okay. Alright, so as you could see here in this diagram, so look at the burial chamber of the pyramid. So the burial chamber is oriented to Tuban in the north. Tuban was the pole star during the time of the ancient Egyptians. And opposite of that, the pyramids, they were oriented to the Orion's belt. So as you could see here, even in the construction of the pyramids, the Egyptians, they have to study the heavens because the pyramids, they were constructed to be aligned to certain stars like Tuban and the stars along the Orion's belt. So here's another illustration of how the pyramids were aligned to certain stars. Like again, during the time of the ancient Egyptians, the polar star or the celestial pole star was Tuban in the constellation Draco, as you could see in this illustration. Okay, not Polaris, but it was Tuban. Okay, then opposite of that, we have the stars along the Orion's belt and even Sirius. Okay, so just look at the burial chamber of the pyramid. So the burial chamber was aligned to those stars, Tuban in the constellation Draco, and the three stars of the Orion's belt, and including Sirius. Okay, fascinating, isn't it? Alright, so you could see here now the shift from Tuban to Polaris. So at present, we have Polaris as our pole star. But during the time of the Egyptians at around 2000 BC, it was Tuban. Okay, they considered Tuban as the pole star. Okay, so isn't that fascinating? Alright, so that's the Egyptians and how they studied the heavens and how they associated the study of the heavens with the pyramids, with religion, even agriculture. Now everybody, I want you to focus on the next slide, and you will find this really fascinating, and you will find this very intriguing, and you might think that some form of alien intervention might have occurred in the construction of the pyramids. Now, the pyramids were located to reflect the constellation Orion. And look at the pyramids at Giza. Those three pyramids at Giza, they represent the belt of Orion. Alright, so I want you now to zoom in on the following. So we have here the three pyramids at Giza, and we have here the three stars of the Orion's belt. So the pyramids at Giza are somewhat associated with the three stars along the Orion's belt. Alright, so isn't that fascinating really? Okay, and how the Egyptians associated even the construction of the pyramids with the study of the heavens. Alright, so here is an aerial photo of the pyramids at Giza. Okay, so you can see here the pyramids of Giza, and we have here the three stars of the Orion's belt. So the pyramids here at Giza, they somehow represent the three stars at the Orion's belt. Okay, so I'm really intrigued by that. So you might think there's some form of alien intervention here. Okay, so that's how the Egyptians studied the heavens and how they associate the study of the heavens in the construction of their pyramids. Okay, now to summarize this part of the lesson about prehistoric astronomy or ancient astronomy, now we have to consider the following. Now the basis of prehistoric astronomy are as follows. Now our ancestors, they started looking up at the night sky, and they started observing and recording the rising and setting of the sun, the moon, and the stars. Then our ancestors, as they looked up, they saw certain patterns of stars in the night sky, and we call them now as constellations. And our ancestors, they believed that these constellations may influence their daily lives. Also, our ancestors, they started observing and recording the annual motion of the sun, the motion of the planets through the zodiac. They also recorded the phases of the moon, and using those ancient astronomical observatories like Stonehenge and the Caracol, they were able to predict eclipses. They also predicted summer and winter solstice. So that's prehistoric astronomy. Now, at this point, let us now zoom in on the contributions of the Greeks to modern astronomy. Now, the Greeks, they were fond of using models to explain how the heavens work. So, through the use of models and naked eye observations, they were the first to use models to carefully and systematically explain the workings of the heavens. So that's what the Greek astronomers did using models to explain the workings of the heavens. And limited to naked eye observations, the idea of using logic and mathematics, they serve as tools for investigating the heavens. Now, unlike the Mesopotamians and the Egyptians who made use of religion to explain the workings of the heavens, the Greeks, they made use of logic and mathematics. And that is a leap forward to the development of modern astronomy, the use of logic and mathematics. Now, aside from using models plus logic and mathematics to explain the workings of the heavens, the Greek astronomers were also skilled in producing astronomical instruments. Now, one good example of an astronomical instrument that they developed was the astrolabe. Now, the astrolabe is an instrument used by the Greek astronomers to measure the altitude of the sun, the moon, the stars, and the planets. So we may consider this as a primitive sextant used by our seamen, by our navy, to measure the altitude of the sun, the moon, the stars, the planets. Okay, that's the astrolabe. Also, the ancient Greek astronomers developed this instrument. This was used by Eudoxus of Knidos. Now, this instrument was used by Eudoxus to simulate the ostensible motion of the planets. Eudoxus tried to simulate the motions of the planets using this instrument that he devised. So the ancient Greeks, they also constructed astronomical instruments to explain the workings of the heavens. Now, speaking of Eudoxus, Eudoxus came up with a model of a geocentric universe that was around 380 BC. Now, Eudoxus designed his model of the universe as a series of cosmic spheres containing the stars, the sun, and the moon. And they were all built around the earth at its center. Eudoxus came up with this model wherein the earth is at the center of the universe, or we call this the geocentric universe. Now, we usually associate the geocentric model with the name Claudius Ptolemy. Alright, but anyway, we will discuss later Claudius Ptolemy. So it was Eudoxus who came up with the first model of a geocentric universe wherein the earth is at the center of the universe. So this was his model of the universe wherein the earth is at the center of everything, and the sun and the 5 visible planets, they revolve around the central earth. So that's the model created by Eudoxus regarding the geocentric universe. Now, Eudoxus has a big problem regarding his model. Now, Eudoxus cannot explain the unusual movement of Mars. So he cannot fit Mars in his geocentric model of the universe. So that was the problem of Eudoxus. Now, Aristotle tried to develop his own model by improving or modifying the model made by Eudoxus. Aristotle borrowed from the idea of crystalline spheres from Eudoxus. The sun, the moon, and each of the planets have a crystalline sphere. The outermost sphere carried all the stars. So that was the model created by Aristotle. Alright, so again, this is just a modification of the model made by Eudoxus. He also placed the Earth at the center of the universe, and the 5 visible planets including the Sun, they all revolve around the central Earth. Okay, so the model made by Aristotle was just an improvised version of the model made by Eudoxus. And Aristotle also encountered the same problem. Now, Aristotle cannot explain the unusual movement of Mars. So, malaking problema ang kanilang na-encounter. They cannot explain the movement of Mars using their models. So as you could see here, the Greek astronomers, they made use of models to explain astronomical phenomena, and they also made use of logic and mathematics, plus the fact that they also produce astronomical instruments like the astrolabe. Now, the Greeks were skilled in the use of mathematics. Now, one good example to illustrate their expertise in mathematics was the contribution of Eratosthenes. Now, you will be fascinated by this, that Eratosthenes was able to calculate the circumference of the earth. And he did that even before Jesus was born. Fascinating, isn't it? So this is how Eratosthenes was able to calculate the circumference of the earth. So he heard about a famous well in the Egyptian city of Syene on the Nile River. At noon, one day each year, that's the summer solstice, between June 20 and 22, the sun's rays shone straight down into the deep well. They illuminated only the water at the bottom, not the sides of the well as the other days, proving that the sun was directly overhead. Okay, so Eratosthenes made use of that well in Syene in Egypt. Alright, so everybody, I want you now to zoom in on this illustration. So we have here this well in Syene in Egypt. So between the days of June 20 and June 22, Eratosthenes would look into the well and he would notice that the bottom of the well is only illuminated and not the sides. So what does that mean? It means that the sun is directly overhead between the days of June 20 to June 22 in Syene in Egypt. Alright, so to continue with the story of Eratosthenes. Now, Eratosthenes erected a pole in Alexandria, and on the summer solstice, he observed that it cast a shadow, proving that the sun was not directly overhead, but slightly south. Recognizing the curvature of the earth and knowing the distance between the two cities, Syene and Alexandria, Eratosthenes was able to calculate the circumference of the earth. So that's how Eratosthenes was able to calculate the circumference of the earth. Fascinating, isn't it? So just using that well in Syene, and he erected a pole in Alexandria, and by knowing the distance between the two cities, Eratosthenes was able to calculate the circumference of the earth. Alright, so just like Eudoxus and Aristotle, Claudius Ptolemy came up with a similar model of the universe by placing the earth at the center And the Sun and the 5 visible planets, they revolve around the central Earth. So this is what we call the geocentric model made by Claudius Ptolemy, by placing the Earth at the center, the Sun and the 5 visible planets, they revolve around the central Earth. Okay, and just like Eudoxus and Aristotle, Ptolemy encountered a similar problem. Now, Claudius Ptolemy cannot explain the unusual movement of the planets, especially Mars. Ptolemy cannot explain the unusual movement of Mars. Now, what is so unusual about the movement of the planets? Now, everybody kindly take a look at this animated illustration. So you will notice typically a planet shifts slightly eastward from night to night, drifting slowly against the backdrop of stars. From time to time, however, a planet changes direction. For a few months, a planet heads back westward before turning back and resuming its easterly course. As you could see in this animated illustration, a planet moves from west to east. Then it goes back westward like so and turns around, going back to its easterly course. So this unusual movement of the planet, especially that of Mars, was observed by Eudoxus. This was also observed by Aristotle and by Ptolemy. So this westward motion of the planets is called retrograde motion. So here's another example. This is Mars. So you will notice in this animated illustration that Mars moves from west to east. Then Mars moves back westward like so, turns around and goes back to its easterly direction. Right, so fascinating, isn't it? So this was observed by Ptolemy, by Aristotle, and Eudoxus. So this is what we call retrograde motion of the planets. Now, what made the geocentric model of Ptolemy different from Eudoxus and Aristotle? Now, Ptolemy had introduced a unique solution to solve the problem of the retrograde motion of Mars and the other planets. So he introduced the concept of epicycles. Okay, so as the planet moves around the Earth, the planet also moves in a circular motion. It is like a smaller wheel turning around a larger wheel. Okay, so let's take a look at this animated illustration. So the blue dot represents planet Earth. So the Earth is at the center, and the red dot is the planet Mars. So as Mars moves around the Earth, Mars also moves in a circular motion. So again, a smaller wheel. Look at the movement of Mars. That's the smaller wheel turning around a larger wheel. That's the orbit of Mars around the Earth. Right? And that's how Ptolemy had solved the problem of the retrograde motion of Mars and the other planets. Okay? So the Earth is at the center. That's the green dot. And the red dot is planet Mars. So as Mars moves around the Earth, Mars also moves in a circular motion. Smaller wheel turning around a larger wheel. Okay? So that's how Ptolemy had solved the problem of the retrograde motion of the planets, especially Mars. So he introduced the concept of epicycles. Okay? So fascinating, isn't it? Okay, so the inclusion of epicycles in the geocentric model of Ptolemy had solved the problem of retrograde motion of Mars and the other planets. And this has become the standard model of the universe. The inclusion of the epicycles had solved the problem of retrograde motion, and this has become the standard model of the universe. So the Catholic Church had accepted this model. This has become the standard model of the universe. Now, this geocentric model of Ptolemy was accepted for several centuries until an astronomer by the name of Nicholas Copernicus came up with another model of the solar system of the universe by placing the sun at the center. Copernicus formulated a model of the universe that placed the sun at the center of the universe rather than the earth at the center. Okay? So we know this now as the heliocentric model of the universe. So Copernicus had placed the sun rather than the earth at the center of the universe. So we call this the heliocentric model. Helio meaning sun, sun-centered model of the universe. Now, using this heliocentric model, Nicholas Copernicus was able to solve the problem of retrograde motion of the planet, especially that of Mars. Now, according to Nicholas Copernicus, retrograde motion occurs roughly when a faster moving planet catches up to and passes a slower moving planet. Now everybody, I want you to zoom in on this animated illustration. Now the blue dot represents Earth and the red dot represents Mars. Now we know for a fact that the Earth moves around the Sun faster as compared to Mars, as Mars is a slower moving planet. So as the Earth passes Mars, we see here from our perspective here on Earth that Mars moves in a retrograde motion with respect to the background of stars. Fascinating, isn't it? So that's how Nicholas Copernicus explained retrograde motion of the planets, especially that of Mars, using his heliocentric model. So retrograde motion, according to Nicholas Copernicus, occurs when a faster moving planet like planet Earth catches up to and passes a slower moving planet like Mars. So we see here from our perspective here on Earth that Mars moves in a retrograde motion. Now, you will notice in the explanation provided by Nicholas Copernicus in explaining the retrograde motion of the planet, especially that of Mars, he eliminated the use of epicycles. He never mentioned anything about epicycles in his heliocentric model. So, in a way, Nicholas Copernicus had contradicted Claudius Ptolemy by eliminating epicycles. Now we know before that Claudius Ptolemy had introduced epicycles in explaining the retrograde motion of the planet, especially that of Mars, in his geocentric model. So Nicholas Copernicus, using the heliocentric model, helped explain the retrograde motion of the planet, especially that of Mars. And he contradicted, by eliminating epicycles, he contradicted Claudius Ptolemy. Okay? Alright, and Nicholas Copernicus came up with his book entitled On the Revolutions of the Heavenly Spheres. And by eliminating the use of epicycles in his model and contradicting Claudius Ptolemy, the church did eventually ban the book in 1616. Now that was really a very interesting story of Nicholas Copernicus. So his book on the revolution of the heavenly spheres, written in 1532, was banned by the Catholic Church. Again, because he eliminated epicycles in his model and he placed the sun at the center of the universe. So this was his book on the revolution of the heavenly spheres. And in this book, he placed the sun at the center of the universe. And he also explained the retrograde motions of the planet, especially that of Mars. Now, what's wrong with the heliocentric model was that Nicholas Copernicus failed to compile astronomical data that would support his model. Now, this guy by the name of Tycho Brahe did just that. Tycho Brahe was able to compile astronomical data. Now, Tycho Brahe was a Danish astronomer known for developing astronomical instruments that would measure the positions of stars. Okay, this was his observatory, and Tycho Brahe was really famous for his astronomical instruments. He built and constructed huge instruments like this quadrant. So this quadrant was used to measure the angular distances of stars, much like the sextant used by seafarers and the Navy. Alright, so that's the quadrant. Alright, so here is again the quadrant that was used to measure the angular distances of stars, much like the sextant of today. Alright, so Tycho Brahe was really famous for these huge astronomical instruments that would aid with his naked eye observations. Now, his observations, the most accurate possible before the invention of the telescope, included a comprehensive study of the solar system, especially Mars, and accurate positions of more than 777 fixed stars. Tycho Brahe was one of the greatest of the naked eye astronomers, and Tycho Brahe made calculations of the position of Mars in 1576. Fascinating, isn't it? Now, what's interesting about Tycho Brahe was that Tycho Brahe also came up with his model of the solar system. Alright, so everybody, I want you now to take a look at this diagram of the model made by Tycho Brahe. Okay, so you will notice that in his model, or the so-called Tychonic model, he placed the Earth at the center of the universe, much like the geocentric model. So the Earth is at the center, the Moon revolves around the Earth, and also the Sun. If you will notice, the Sun also revolves around the Earth. But everybody, look at the Sun. So all the planets, okay, Mercury, Venus, Mars, Jupiter, and Saturn, they all revolve around the Sun, much like the heliocentric model of Nicholas Copernicus. Alright, so this was the so-called Tychonic model of the solar system. So it is like the combination of the geocentric and heliocentric models. So in this Tychonic model, the Earth is at the center. The Moon and the Sun revolves around the Earth. But the 5 visible planets, they all revolve around the Sun. So here is a combination of the geocentric model and the heliocentric model. So this was the model made by Tycho Brahe, the so-called Tychonic model of the universe. Now, even though Tycho Brahe was really good in his naked eye observations, he was not good in math. So he needed some mathematical assistance to aid in his calculations. So he hired someone by the name of Johannes Kepler. But Tycho Brahe had some temperamental issues. So Kepler and Brahe did not get along really well. Okay? So Tycho Brahe apparently mistrusted Kepler, fearing that his bright young assistant might eclipse him as the premier astronomer of his day. Kasi magaling si Johannes Kepler sa math. So medyo na insecure si Tycho Brahe. Alright? So he mistrusted Kepler, fearing that his bright young assistant, kasi matalino tong si Kepler, might eclipse him, baka masapawan siya as the premier astronomer of his day. So he let Kepler see only part of his voluminous data. Hindi niya masyadong pinagkatiwalaan si Johannes Kepler. Okay? So that was Johannes Kepler and Tycho Brahe. Now, as you could see, the working relationship between Tycho Brahe and Johannes Kepler was not really good. And when Tycho Brahe died, Kepler was really joyous. Why? Because Kepler got access to Brahe's voluminous astronomical data. So when Tycho Brahe died, Kepler got access to Brahe's astronomical data, and using his brilliance in mathematics, Kepler formulated the laws of planetary motion using the data provided by Tycho Brahe. So that was really interesting. So when Tycho Brahe died, Kepler used Brahe's data to develop the three laws of planetary motion that explained the movement of the planets. So at this point, let us now go into the details of the laws of planetary motion by Johannes Kepler. Okay, this is the first law. Now, according to Kepler's first law, all planets move about the sun in elliptical orbits, having the sun as one of the foci. So, according to Johannes Kepler, a planet moves not in perfect circles as mentioned by Nicholas Copernicus, but a planet moves in an elliptical path or an oval-shaped orbit, as you could see in this animated illustration. So all the planets, including our Earth, all the planets, they move around the sun in an elliptical path. So that was Kepler's first law. Now, because a planet moves around the sun in an elliptical orbit as mentioned in the first law, there are times wherein the planet is closest to the sun, and there are times wherein the planet is farthest from the sun. So, the point wherein the planet is closest to the sun is called the perihelion. And that point wherein the planet is farthest from the sun is the aphelion. Now, everybody look at the speed at which the planet moves around the sun. As it approaches the perihelion, the planet speeds up. And when the planet approaches the aphelion, it slows down. Alright? So a planet moves most rapidly when it is nearest the sun or the perihelion. And a planet moves slowly when it is farthest from the sun or the aphelion. And this was the basis of Kepler's second law of planetary motion. Kepler's second law of planetary motion describes the speed of a planet traveling in an elliptical orbit around the sun. Okay? So the speed of the planet increases as it nears the sun, and it decreases as it recedes from the sun. Alright? Okay, so as you could see here in this animated illustration, so when the planet approaches the perihelion, the planet speeds up. And when the planet approaches the aphelion, the planet slows down. Okay, so that's Kepler's second law of planetary motion. Now, what about Kepler's third law of planetary motion? Now, according to Kepler's third law, how long a planet takes to go around the sun is related to the planet's mean distance from the sun. Now, everybody, I want you now to take a look at this animated illustration. Now, the yellow dot represents the sun, who is at the center of the universe. The blue dot represents planet Earth, while the green dot represents the red planet Mars. Now, we know for a fact that the Earth takes about 365 days to complete one revolution around the sun, while Mars takes about 686 days to complete one revolution around the sun. Now, knowing that Mars is farther from the sun as compared to Earth, Johannes Kepler concluded that the farther the planet is from the sun, the slower is its orbital speed. As you could see in the planet Mars, Mars takes longer for it to complete one revolution around the sun as compared to Earth. Alright? Okay, so let's take a look at the planet Jupiter. Now, here is the mathematical application of Kepler's third law. Okay, in calculating the revolution of Jupiter around the sun. Now, based from this mathematical calculation of the revolution of Jupiter around the sun, Jupiter takes about 11.8 years to complete one revolution around the sun. Okay, knowing that Jupiter is farther from the sun as compared to Mars. Mars takes about 686 days to complete one revolution. While Jupiter is farther from the sun as compared to Mars, Jupiter takes about 11.8 years to orbit the sun. Okay, so that's quite fascinating. Now, everybody, let's take a look at Venus. Now, Venus takes about 224 days to complete one full circle around the sun, knowing that Venus is closer to the sun as compared to Earth. The Earth takes about 365 days to complete one revolution around the sun. Alright, so that's Kepler's third law. The farther the planet is from the sun, the slower is the orbital speed of the planet. Alright? Okay, so that's Kepler's third law of planetary motion. So again, let's take a look at Jupiter in this animated illustration. So Jupiter, being farther from the sun as compared to the inner planets, Jupiter takes about 11.8 years to complete one revolution around the sun. Okay, so the farther the planet is from the sun, the slower is its orbital speed. Okay? So that's quite fascinating, isn't it? Alright? But the problem with Johannes Kepler is that he was able to describe the movements of the planets, but he cannot explain the reason for such behavior of the planets around the sun. So that explanation will be provided later on by Isaac Newton. Well, I guess that's about it for episode 5 of Space, the Final Frontier. Sana marami po kayong natutunan sa episode na ito. Now, in our next episode, episode 6, we will study the contributions of Galileo Galilei, Sir Isaac Newton, and Edmund Halley. Now, if you have any questions or comments or reactions about this episode, please do not hesitate to type in your questions, your comments, or your reactions. We would like to hear from you. Gusto po naming malaman ang inyong mga reactions o yung mga katanungan or comments about this episode. Please like and share this video para makatulong po tayo sa mga estudyante na gustong mag-aral ng siyensya. Pa-shoutout po sa mga students ko from 11 STEM at mamimiss ko po kayong lahat. And pa-shoutout sa mga suki natin dyan, mga ka-spacers na laging nakatutok sa ating programang Space, the Final Frontier. Sana wag po kayong magsawang tumutok sa ating programa at marami po kayong matututunan dito, especially about the sciences. Kaysa manood po kayo ng mga teleserye, dito na lang po kayo tumutok sa ating programang Space, the Final Frontier. Okay, so maraming salamat. Thank you po for watching. And in behalf of the officers and crew of the Bedan Society of Young Astronomers and to our administrators at San Beda University, this is your professor, Professor Jun Cahigal, saying, live long and prosper. And I will see you in our next episode of Space, the Final Frontier. Always stay safe and goodbye everybody. Good night.
There she is. NASA's Voyager 1. Launched in 1977.
But that's just very small potatoes compared to what the Earth is involved with and is about.
We choose to go to the moon in this decade and do the other thing, not because they are easy, but because they are hard.
It's one small step for man, one giant leap for mankind.
Choose to go to the moon in this decade and do the other thing, not because they are easy, but because they are hard. Because that goal will serve to organize and measure the best of our energies and skills. Because that challenge is one that we're willing to accept, one we are unwilling to postpone.